started. So the next bit we're going to talk about vectors. Vectors are different from scalars because they have a magnitude and a direction. And really, although this is called conceptual calculus-based physics, what we really do a lot of is vectors. Vectors are kind of everywhere in this. So if I have just a magnitude, if I say it's 25 degrees, that's a scalar. It's not got a direction in a room. I can say it's 25 degrees over there, but that is if you like, a direction to a point in space. It's the over there bit that's the vector, not the 25 degrees that's the vector. I could say the temperature difference is between 75 and 50 is 25 in that direction. That's a vector. That's a temperature gradient. That is a vector. So it's not sufficient to say, does it have a positive or negative sign? Because, you know, I can have minus temperature and plus temperature, and it's still a scalar. The best thing to do is say, does it have a direction in a room? If it has a direction in a room, then it's a vector. So does mass have a direction in a room? No, it doesn't. So it's a scalar. What about weight? Does weight point in a direction in a room? You bet it points downwards, doesn't it? So that's a vector. And so on. So if we go through what we know at the moment, velocities, vectors for sure, yeah? Speeds, not. Accelerations, for sure. Displacements, for sure. Time, no. They talk about the arrow of time, but that's, you know, that's advanced stuff, and it's not for us. We're going to get onto mass. Will not have. Force will have. We're going to start talking about things like momentum will have. And we can go on and on like that. Pretty well all the way through Physics 1 and Physics 2, you need to be asking yourself, is it a vector or is it a scalar? And it gets kind of involved. Sometimes, especially in Physics 2, there's things that's not obvious unless you really think about where it comes from, whether it's a vector or a scalar. The thing is that vectors and scalars sum differently. If I just add two scalars together, it's arithmetic. I just say 12 plus 5 is 17. But if I have something that's a vector that's 12 units long and another vector that's 5 units long, then the addition depends upon their relative direction. So if I have a vector, yeah, that vector is 12 meters. But my other vector, well, that other vector is 5 meters. Well, that effect is not 17 meters. It's clearly not. So the two numerical values, 12 and 5, add to 17. But your answer when you're adding two vectors together is not that numerical answer. You've got to take the direction into account. And if that's what physics wants us to do, that's what we've got to do. It's not just like we're making the sums more complicated. We need that to get the right answer. So, okay, we start off by saying what's the difference between the vector and a scalar? And a scalar has a magnitude but not a direction. And so good examples are temperature and mass. And a vector has both a magnitude and a direction. And that's displacement, velocity, and acceleration, for example, over what we've done so far. Magnitude being a size, you know. So we're going to start talking about 2- and 3-dimensional things. Let's start with 2 dimensions. And there was good old Descartes, French mathematician, philosopher, who divided the universe up into actually 3 dimensions, x, y, and z. In 2 dimensions, we tend to talk about x and y. And he said, look, you know, you can pinpoint a point in space by giving its x-axis coordinate and its y-axis coordinate relative to some origin, taking into account these orthogonal 90-degree axes. We could have a system where we had the axes might not be at 90 degrees to each other. Wouldn't be as useful. In a coordinate, Cartesian coordinate system, our axes are at 90 degrees to each other, and it works really well. It's not the only way, though. There's another way called plane polar coordinate system, where we basically take the distance from our origin to the point of interest. So we just take the straight distance, and then we take the angle from some reference axis. And so we put the distance first and the angle second. So there's some rules, isn't there? The first one was we put our x coordinate first and our y coordinate second and our z coordinate. And in this case, we'd have our distance. This is only in 2 dimensions. We'd have our distance from the origin, and then we'd have our angle. Why have 2 of them? So when I was a student and I got a new way of doing something, I'd kind of roll my eyes and say, oh man, just make him work. Can't we do this using the old way? You can, using the coordinate system, the Cartesian coordinate system, but there are some circumstances whereby life gets a whole lot simpler if you use the new technique. For instance, if I have just a circle on a page, and I put down all the x and y coordinates for points on that circle, and I put them as a table, I suspect that you might not even recognize that they are a circle. But if I put down the plane polar coordinates, you would see that the distances are all the same, and the angles increase steadily. It's pretty obvious it's a circle. So you use different tools for different times, and it works out quite nicely. So we say a coordinate system is used to specify locations in space. A coordinate system must consist of a fixed reference point called an origin, a set of specific axes or directions, and instructions. You know, put the x down, then put the y down, with a comma in between. They're the instructions of how you work it. And we can play with this a little bit. A point represented by 3, 4 in a Cartesian coordinate system expresses as a plane polar coordinate system. So again, we visualize 3 points along the x, 4 points along the y. It's positive and positive, so it looks like that. Now I want to think about it. I'm going to change coloured pens to make it a bit clearer. Oh, come on. I'm going to change coloured pens. Stop. I'm going to change colour of my pen to make it a bit clearer. No, that didn't work. I'm going to change the colour of my pen to make it a bit clearer. There. And now I'm looking at this. I'm looking at that. It's the same point, but it's referenced in a different way. And you can see, just from geometry, you can see that my r is equal to Pythagoras, the square root of x squared plus y squared. That's pretty straightforward. And so r is equal to the square root of, what was my 3? My x was 3 squared, and my y was 4 squared. So that would be the square root of 9 plus 16, which equals the square root of 25, which is 5 meters. And then my angle, and this is where your trig comes in. So tan the angle equals opposite over adjacent, which equals the opposite, which is the y coordinate, which is 4, over the adjacent, which is 3, which gives me, if I go to my calculator, which gives me, and of course I want to check to see what I'm in. I'm in degrees. Good, I'll stick with degrees then. I'm going to go second tangent, and I'm going to go 4 divided by 3, and I'm going to get 53.13. degrees. So I get 5 meters and 53 degrees, 5 meters and 50 degrees. So it'll be C of that choice on there. And that's just using some math that you already know in a new situation. It's like, this is a bit that's kind of important. For a number of reasons. One is because they're actually useful in their own right, and the second one is they're useful because they're the better you can draw a vector diagram, the better you can work your problems. Okay. So, how do we do a vector diagram? We just draw the vectors one after the other if I want to add them, which I often want to do, then basically I can draw the tail of the second vector on top of the head of the first vector. That's the process of addition in vector diagrams. So let's say that I'm dealing with vectors that are to do with displacement. So I had a journey and it consisted of moving, in this case it would be to the east, and then I went to the northeast, and then I went at some angle to the, it's not quite northwest, it's more like west by northwest, and then we have northeast, and then we have west. So we have, I don't know, 5 bits to our journey. And we can add and get the overall effect, the resultant. It's called resultant. I get the resultant by replacing this journey. So my resultant is a vector. It has a magnitude and it points to where you end up. And the tail of the resultant is matched to the tail of the first part of your journey. And the head of the resultant is to the head of the last part of your journey, and it's a straight line going between one and the other. So that works out. What's a little bit more uncomfortable is that I can apply this technique to vectors that don't necessarily represent directions and distances in space. So let's say I had a block, and let's say I had a 6 Newton vector in that direction, and a 4 Newton vector in that direction, and a 3 Newton vector in that direction, and a 7 Newton vector in that direction. Now, Newtons don't go anywhere. They're just a strength of something. It's a force. And yeah, I can imagine drawing a 2-dimensional, I can in fact draw a 2-dimensional vector diagram, which is kind of like in Newton space. And so the first thing I'd say is, if you can draw your diagrams with the arrows to the appropriate length, it intuitively helps tremendously. So I tried to draw the 3 as the smallest, I tried to draw the 4 as the next, the 6 as the next, and the 7 as the next. I think my 6 should be a little bit longer than I've drawn it, so I'll extend that. But it just gives me a sense of, oh, I'm kind of going to go in the right direction. But then what I would do is I would get my ruler, and I would get a piece of paper or a protractor, and I would say, well, okay, let's add these guys up. And I would say, well, let's do the first one is the 3, so I'm going to draw that as it is. 3 units. What shall I use for my unit? Let's use 1 centimeter equals 1 Newton. So I do 3 in that direction. And then I want to add on the effect of the second one. Well, let's call the second one 7. So I draw a line down here, and that's 1, 2, 3, 4, 5, 6, 7 units long in that direction. That's those two taken into account. Now the 6, okay? The 6 kind of goes in that direction, so it goes up like that. I've exaggerated that a bit. It's like that. 1, 2, 3, 4, 5, 6. And then my last one is the 4, and the 4 kind of goes up like that. And that's 1, 2, 3, 4. And so my resultant, I'm going to change coloured pens for this. My resultant starts here and ends, starts here and ends there. And I can actually, 1, 2, 3, 4, probably 5 and a bit. 5 newtons, and that's my resultant. It started with its tail on the tail at the beginning, and it ended with its head on the head of the end. I can do that for a whole ton of stuff. I can do that for electric fields. I can do that for gravitational fields. I can do that for impulses and momenta. I can do that for a whole bunch of physics. It really, 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 really helps. So it's a really useful skill. And what I want you to know at this stage is the process of adding these guys together. So this is a typical kind of test question. I give you two vectors. Sometimes I tell you what they are, sometimes I don't tell you what they are. And then I say, well, find the resultant. And what that means is add them together. I suppose I should say, find the resultant of adding these two guys together, if I'm honest. So let's call this one A and this one B. I would say draw A plus B. And so what you do, and the most common mistake I see is people try and use this diagram to get the answer, which I think is a mistake. I think you just move to the side and you just draw A the way A is drawn. And then you get this guy and go to the side and you draw B the way B is drawn. Put the tail of B on the head of A. So this is A and this is B. And then my resultant is like that. Little arrows on the top mean vector. Used to be all the textbooks had little arrows on top of vectors, and that became just a pain to typeset, so they started using boldface. When the computer typesetting came out, they said, why don't we just put bold? So they put boldface, and then people like me started using boldface. But then you quickly realize that you can't write with boldface very easily. So you start putting arrows back on the top of your vectors. So it's good to have arrows on top of vectors. That's basically the skill. I use a ruler or a straight edge and I slide it across my page and draw the arrow. Then I take the ruler and I slide it across the edge and I draw the arrow, and then I draw my answer in. This could be adding velocities together. It could be adding forces together. It could be adding displacements together. It could be adding accelerations together. But the process of addition is you put the tail of the second thing on top of the head of the first thing, and you go from the beginning to the end. What about subtraction? Subtraction is basically adding a negative when you think about it. If I have vector A minus vector B, that's like vector A added to minus vector B, because I know how to add. The process of addition is put your tail of your second thing on top of the head of your first thing. That's how you add. So if I just, rather than using vector B, use vector minus B, I can just add it. Well, if this is vector B, vector minus B is just in the opposite direction. Same size, but opposite direction. So for this one, if I did this, I'd say find B minus A. Now here, the order does matter. Well, the order doesn't matter as long as you do it right. But I like to start with B, and then I like to do them in the order that they're written. So I'm going to do B. And then I'm not going to add A on. Adding A on will be that. That's not what I want to do. I'm going to add minus A on, and minus A is that. It's minus A. It's the same thing as A, but in the opposite direction. Same magnitude, opposite direction. So this is B, and this is minus A. So my resultant is that. Res. What do I look for in grading? I look for, are the arrows in kind of like the right direction? Not to a degree. I mean, within a few degrees. Is it 5 degrees either way? Is it clearly that you just pulled your rule across and did it? Or are you pointing off towards the ceiling for some reason? And secondly, do you have arrows on all these lines? Because they are vectors, so they need arrowheads. If it's just a line, it's just a line. It's not a vector, so I'm picky about that. And then the most common mistake is people either put the arrowhead at the wrong end of the answer, or they don't mark the answer, or they put don't put an arrowhead on the answer. And those are that's not good. It's a nice, easy skill. If I'd said, let me show you something that's a bit beautiful now. Supposing I said B minus 2A. I'd draw my B. I'd take A away. I'd take another A away. So can you see how we did that? We just added 2 negative A's. It's a nice skill. It's a bit of practice, but it's easy points once you get the hang of it. Yeah? So this is what I just did, actually. So if you have 3A is 3 times, it's the direction of A 3 times longer than A is. 5A would be the direction of A 5 times longer than A is. So question for you, characterize these as either being polar or Cartesian coordinates. So, how are we doing? Let's stop it here, see what most people said. Pretty well everybody's saying A, a couple of people saying C, but let's have a look and see what's going on here. So that's going to be Cartesian. So we have C. That's going to be polar. That's going to be polar. And that's going to be Cartesian. So hopefully that's there. C, PPC, yeah, it's A. Agreed? Can you, using a vector diagram, find the resultant of these displacement vectors? What I'm going to do is I'm going to have you a minute to have a go at it, and then I'm going to draw it myself. So this is find the resultant of these displacement vectors. And again, in a test, I would say, I'm more likely to say, add these 2 vectors together, be more definitive about it. I'm using here resultant to mean addition, and clearly when I say, well, what's the resultant when you do this and this, it's not quite the same. So bad language on my part on this. For addition, I just basically got to draw one of them. I'll draw my B first. And then I got to add on, so put the tail of the second one on top of the tail of the second one on top of the head of the first one. And try and get to the right length. And then... So what I would look for in the test, let's be clear about this on the test. I would look to see, are these roughly in the right direction? And are they approximately the right length? So I'm not going to go to the millimeter. I'm going to go, is the methodology right? And then the second thing is I will look for your arrows and make sure you do have arrows and you don't just have lines, because this is a vector, so it needs an arrowhead on, and that's a vector, so it needs an arrowhead on. And then did you clearly mark the answer, maybe vector C or maybe vector resultant, and does that have an arrowhead on? And if it does not, then it's not a vector. So that's what I'm concerned about. Was that a question or a comment? Or, no?
Oh, no.
Okay, cool. Okay. So it's not that this is not an exercise in how precise are you. I'm not going to say, oh, you're 2 millimeters off, therefore no points. But it can't be that it's kind of like over to one side, and that's kind of like that, and then you go like that, and you go, well, hold on, I just turned things to one side. It's not going to work. It's going to be, you've got to take your ruler and slide it, and get a good approximation to it. Using a vector diagram. Can you have a go at that one for me as well, please? We're back, and for these, remember, I'm looking for the methodology as much as anything. This is B minus A. Well, if that's plus A, this is minus A. So this would be vector B, and this would be vector minus A. So my resultant, so I'll put down B minus A. And that would be what I'm looking for on that question. Simple as that. You don't have to worry about what scale do I use for the conversions. Just take the arrows lengths and move them to one side. Can you ever go at that one for me, please? So on this one, we have vector A. So let's just, I lose my pen on this thing because it's such a small little spot. There's my vector A. And then I'm going to add on 3 vector B's. So there's 1 vector B. You can draw it as one continuous arrow if you want. I prefer to do it as like 3 individual little vectors because then I can just double check it. So there's my A. And there's 1 vector B. There's another vector B. And there's a 3rd vector B. And then my answer would be, I'm probably in a test, this is my A plus 3B vector. Probably in a test I would make sure that that one is really well put in. I'd make sure that that one is really well put in. I'd make sure that that one is really well put in. Even if it doesn't look as pretty. Because I don't want to lose points because I didn't put the little arrowhead on the end. I want to say, hey, I know what I'm doing. Last one, I'm going to do this one for you. So this is 2A. So we go, there's 1A, and there's another A, and then minus B. Well, B goes that way, so now B goes that way. So this would be A, and then minus B. And so my resultant, my answer would be that, and this would be 2A minus B. And again, I would be careful to make sure that one had a big, nice arrowhead on, and that one had a big, nice arrowhead on, and that one had a big, nice arrowhead on. Cool? Yes?
Doesn't it order matter which way you do it? So if you do negative B and then you do 2A.
So if I did my negative B, so my negative B goes like that. As long as now you're going to add the 2A. You can't add the 2A to that end. You've got to put the tail of the second on top of the head of the first. So I do A, and then I get, which is the same answer. Okay. Yeah, if you look at it, they're parallel to each other, yeah? Mm-hmm. Whereas what I worry about is people will put the minus B, and then when they start off stemming from here, you know, when they put the second one, then it's not addition. But the actual order, as long as you do it the right way, is fine. Yeah, yeah, that's really good. Cool. So I'm trying to cut down on, I'm trying to make the test a little bit briefer, but I really do like having a question just like that on the test. Later on, we have a vectors lab, and typically with the vectors lab, I give you more complicated things where I say 7 newtons and 15 newtons and 5 newtons at certain angles. And then you decide what scale do I want to use, and you use a protractor. In the lab, I think that's quite appropriate. For a test, I'm not so worried about it. I just want to know, do you know how to add and subtract vectors? Multiply them by a constant. Next, trigonometric expressions. So okay, let's go back to this journey. Let's do it using math. And the problem is it gets tedious and a bit hard. First of all, why do we not use diagrams? They work. And that's because there's a little bit of uncertainty about where that end is, and then we're a bit more uncertain about that one, and we're a bit more uncertain. I mean, as individuals, we might think we know, but if we compared the class's results, they would get more and more scattered as we had more and more steps. So vector diagrams don't work so well if you're doing like 5 different steps. My dad was a navigator and flew basically all over Europe using a piece of paper with some parallel rulers and a protractor. But he didn't do 5 steps. He said, we're going to fly from here to Paris, and he got the heading, and then when they got near Paris, they looked around and said, oh yeah, Paris is actually over there. So they went to Paris. And then they said, all right, from Paris, we're going to go to Brussels. And they said, we'll go in that direction. They can't see it, but they fly in that direction, and they look, oh yeah, Brussels is on that side. So they're not blindly doing 5 points, and then, you know, where's Prague? It's like, so they're doing it bit by bit. So when you get more and more steps, you get more and more uncertainty. Okay, but we could do it mathematically, and it would involve a fair bit of trig, I guess. We have these weird angles, and it's a bit of a mess. And I bet if I asked the class to do that, including me, it'd take us a long time. If I asked you to find me the length of this answer and the angle to the horizontal, I think x-axis, I think we could do it, but it'd take us a long time. It'd be a real pain. With many slips in the way, because it's just, those angles don't lend themselves to analysis. We like things that are kind of like less than 90 degrees, and we like things to be like on a nice grid system. So then along came somebody who's really good. And what they said was, well, okay, if that's what we like, let's give ourselves that. So basically what it said was, okay, imagine putting the y-axis and x-axis at every point. And let's not worry about, let's break every vector down into an x bit and a y bit. And then we can get our answer by simply adding up all the x bits, be they positive or negative, and getting an overall effect, and then adding up all our y bits, be they positive or negative, and we'll get our answer really well. What we do is we do the same process over and over again. We change any old vector in any old direction into an x component and a y component. We get good at that, the rest is storms. Works out really nicely. And this is one of those things where it looks easy, and you find there's all these little pitfalls that you don't expect. Certainly I found there was all these little pitfalls I didn't expect. So what we say is we can do a more accurate job of adding, subtracting, scaling, scalar multiplying, or scalar dividing by applying trigonometry to vector diagrams, but the math can be tedious and long, so it is better to use vector components. So this is saying my answer, my vector component A, is the same as my x component added to my y component. Now, I've not drawn them as adding here. I've not drawn the vector diagram, I'm just representing what they are. That is my x component. That is my y component. If I take my x component and I add it to my y component, I get my answer. And what I'm saying is, if we get really good at finding the x component and the y components for any old vector, we can then add all our x's together, get our x component of the answer, add all our y's together, get the y component of the answer, and we got our answer. It's great. It involves usually sines and cosines, Pythagoras. So if I say, well, how long, so this is not a vector, this is a scalar. How long is this x component? Well, there's my angle, and there's an adjacent, and there's a hypotenuse. And we say adjacent over hypotenuse equals the cosine of the angle, so the adjacent equals the hypotenuse cosine of the angle. Oh, so the length of my x coordinate is the length of the original vector times the cosine of that angle, using a bit of trig. And for my y-axis, oh, well, look, the length of my y-axis component is the length of the original vector multiplied by the sine of the original angle that I dealt with. Now, notice, this is the opposite of this angle, which is the same as what I want in the y component. So I'm choosing to use cosine for the x and sine for the y because I'm using the same angle to define both of them. You could have said, oh, this is gamma. And you could have said, oh, well, this is a cosine gamma. That is also correct, as long as gamma plus theta equals 90 degrees. Then that'll work. So what I'm saying is you don't need to always use this angle. You can use that angle. And if I use that angle, then this y-axis is a cosine of that angle. But it's the sine of this angle theta. So you can't just memorize a cosine theta, a sine theta. Because maybe I won't always give you the angle with respect to the x-axis. Maybe I'll give the angle with respect to the y-axis. So it looks trivial, but you gotta get it practiced. The other thing, and this drove me crazy, was that the original vector is always the hypotenuse in these triangles. It is in the diagram, it's the hypotenuse. But when you're drawing these diagrams, the original vector, you must always draw it as to make it the hypotenuse. So sometimes we're working on a slope and we'll have a weight, and I want the component of that weight along the slope. And the question is it that? Or is it that? And when I first began, I wasn't clear about that. And sometimes I draw the longer arrow and do my math, and sometimes I do the shorter arrow and do my math. And I kept thinking, when I looked at the back of the book and got the answer wrong, I think, oh, I did my math wrong. And I correct my math. But I was not doing my math wrong. I knew my sine, my cosine, and my tangent. It was my diagram. It was my visualization that was wrong. I was thinking the right angle was here, but that would make my component longer than my original vector, which makes my component the hypotenuse. And that can never be true. So you've got to practice. And I have for you, I just put it up online, I have for you a worksheet. And it basically is just drawing out what you think is the right component diagram. First of all, when you're x and y, but then when you're on a slope. It's when you're on a slope that people have issues. And can you draw the right diagram? And these, all you do is you measure, you get a ruler and you just measure how long the things are. You're not even using trig in this. And if there's a problem with this, it's your diagrams you need to work on. If you're getting these right and there's still a problem, it's your trig you need to work on. But I found actually that most people, it's the diagram, their visualization is wrong. It's not that most people can learn their sines, cosines, and tangents. Sometimes people are really slow with them, which is an issue. But most of the time, people can learn them. So let's do an example. A football is kicked at 10 meters per second. So that's the speed it's kicked at, 10 meters per second, at an angle of 30 degrees elevation above the horizontal. Notice that language, please. 30 degrees elevation above. 30 degrees elevation above. What is the horizontal component of velocity? So I think this is important. I think you need to draw this diagram. And you need to draw in what the Vx is. So the length of the horizontal component would be Vx is equal to, think about your trig. Let's just do it down here for once. Cosine theta equals adjacent over hypotenuse. I want the adjacent. I got the hypotenuse. I need the cosine. Sine theta equals opposite over hypotenuse. Now, I'm using the adjacent, so I'm going to say, oh, Vx is equal to 10 cosine 30 degrees. So Vx is equal to, need my calculator out. And I'm getting 8.668. And it's going to the right, so let's call that a positive. Cool? Cool. What angle of elevation of a rooftop when it has a horizontal component of displacement and a vertical component of displacement? So this is like, I've done my sum and I got all the horizontals added together, got all my verticals added together. I end up with this bit. I know that that horizontal is, let's do it a bit shorter, is 10 meters. And I know that the vertical component is 20 meters. Here's my building. I want to know that angle. I say, well, tan theta equals opposite over adjacent, which equals 20 over 10, which equals 2. So theta is equal tan to the minus 1 of 2, which equals, and again I just eyeball and check to see that I'm on degrees. I go second tangent 2, and that's going to equal 63.43 degrees, so 63 degrees. So imagine I have a complicated problem. I get the x and the y component for the first vector, I get the x and the y component for the second vector, x and the y component for the third vector. I add all the x components together just using arithmetic. I add all the y components together just using arithmetic. I then have the x and the y component for my answer. I want to find the actual value of the answer, use Pythagoras. Want to find the direction of the answer, use 10 to the minus 1. It makes life so much easier. It's great. Here's a question for you. Determine AX and AY. Can you do that for me, please? Let's stop that there. So stop that, and let's have a look and see what we got. And mainly people are saying D, so let's have a look at this. So basically what I would say is, so the first thing I do is I want to visualize this. So the first thing I do is want to visualize it. So that is my x component. That is my, if you like, my delta, my xx, delta xx, let's call it. And this here is my delta xy. So I would say my delta xx is equal to 7 cosine 25. And my delta xy is equal to 7 sine 25. So my delta xx is equal to, and I come along here and I'm going to go, okay, this is going to be 7 cosine 25. And that's going to be 6.34 meters. And then my delta xy is going to be 7 sine 25. And that's going to be 2.96. This would be delta xy equals 2.96 meters. So rounding and doing what I need to do, that's going to come out to be, let's have a look, it's going to be 6.3. It's going to be this guy here, D, isn't it? It's going to be the right answer. People do get confused about the x and the y, and I can't show you this on the video, but basically, well, I can actually. So that's the basic scenario. Now, it might be that I have things like that. Oops, that's not going to work. Like that. It may be that, you know, I'm working down a slope, so I want a component down a slope, and I want a component perpendicular to a slope. So it may be it's not this nice looking triangle, but basically I might give you that angle or I might give you that angle. So it can get a bit confusing. So here's a trick that I've figured out, and that is, okay, let's say I give you that angle there as usual. If you put your hand, so your thumb is like that and your fingers are like that. You put your thumb on what you want and your fingers on what you have, or you put your thumb on what you have and your fingers on what you want. It doesn't matter. And you say, if I'm using the angle between, if I was given this angle between, the component would be a cosine of that angle. But if, as in this case, the angle between is not given, it's the what, complement of the angle, the other bit to the 90 degrees, then it's the sine of that complement. So if this was 47, this would be sine of 47. If this was 62, it would be the sine of 62. So put your finger on what you want, and you put this little V on what you want and what you have. And if you're using the angle in between, it's a cosine. And if you're not, it's a sine. And you can kind of, you need to double check that in your head, but I think it pretty well works all the time. Okay. So this is where we've got our answer. We did 4 of those and we added them together. Here's our answer. Can you do that one for me, please? Determine the magnitude of the resultant. So we're back. Let's stop this and let's see what most people are saying. Most people are saying C on this one. Let's have a look. So basically I have 4 meters and I have 6 meters, and so I want to get the resultant, which is that guy, and there's my angle. Let's call that A. So I say, oh well, A is equal to the square root of 6 squared plus 4 squared, which equals the square root of 36 plus, let's not rush, 36 plus 16. So A is equal to the square root of 4652, which equals, and if I come along here, turn you on, clear, second, square root of 52, enter, 7.21, so that equals 7.21 meters. And then for the angle, say tan theta is equal to the opposite, which is going to be the 4 over the adjacent, which is the 6, which gives me that theta is equal to tan to the minus 1 of 0.66. So I come along, clear, I go second tangent, 0.66, and I get 33.42, 42. Yeah. So theta equals 33.42 degrees. So those are my 2 bits, and with a bit of rounding and all that kind of stuff, 33. So it's C is the answer on that one. Okay. Cool. I'm going to draw a line there. So IJK vectors will not be on this first test, it will be on the second test. A little bit behind, but that's fine. I want to just talk to you for a minute before you go. First of all, when I post something online, is it sending you an email to say he posted something? So when I posted something on Friday or Saturday, hopefully you got an email saying that it's there. Okay? So watch out for that. Secondly, look back at the old test. There's a lot of old tests. They might not finish exactly where my test finishes, because as you see, we stopped a bit early this time, you know. But I want you to go through those old things, and just, if it's not in that one, look at the next one, or, you know, don't come to me and say, why is there no 2-dimensional motion on this? You know, you didn't teach us that. Yeah, because in that semester I had the test at a different time. So use your intelligence about sorting it out. You'll see the same materials come up over and over again, different questions, the same skills. And so I would use some of those practice tests to just study by, but I would save at least one of them and do it like the day before and say, how did I do? You know, you got the key, you got the thing, just do the test like it's a test and just see, how did I do on this? I hope you all do really well. This is a test where people tend to do better on this one than they do on some of the later ones, because it's more bookwork, there's less visualization and more bookwork. You have a chance in this test to really have a solid foundation. But if you're kind of coasting to see how well you can do, and you don't do very well, you're going to have to make it up in those other tests. So really try to hit a home run in this first test and score a lot of points, because it's a lot of quite accessible stuff in here. If you have questions, I'll be in office hours, of course, today and tomorrow and the next day. And good luck. And I'll see you guys in lab if you're in lab with me. Oh, before you go, hold on. Sorry, I meant to do this, so let me go through this. Let's go. These should be in order, so let me go by people who've moved, I'm sorry. So, Judith. Yeah, there we go. Grant. Desiree. Free. Tyler. Daniel, I think it is. Oh, sorry, no. I need my glasses as well. Let's look. Wrong hole.
Yeah.
Did I say that right?
Yeah.
Juan. Jessica. Miriam. Yes, sir. Hunter. Maria. Annalise. Nicholas. This is like it's going to work now, isn't it? Michael. Yeah, so Michael. Michael. Trent. Feels like two. Noah. Alright. Chase. Ian. Joshua. William. Sergio. Anthony. Timothy. Samuel. Oh, hey, oh, George. Which you prefer? Okay, cool. Lender. Oh. Leo. Okay. Keep reminding me, okay. Elizabeth. Grant.
Grant left, I think. I have a question.
Yep.
What would this be? Because it's wrong.
So this is square kilometres, so it's 10 to the 3 in one direction, 10 to the 3 in the other direction, so that's going to be 10 to the 6.
Did I not write that down? I did. Of course I did.
Yeah.
Mistake.
Okay.
Do you post these with the work that you did in class online?
When you say...
Like the notes that you put up on here?
Just the video.
Oh, the video.
Oh, the notes online are very different. Like there were 2 problems today that I did
Yeah.
that were not on the notes.
You got, I think what you got is the most recent version. I've got to put them on this computer here.
And then the most recent version actually has different formulas that you use when you solve for the kinematics.
When you say different equation, what do you mean?
Like, you know when you solved it, we only used VF is equal to VI.
Oh, there were different problems.
Yeah.
Oh, yeah, different problems.
Yeah.
I think I went through and I sorted out why am I always using VF equals VI plus AC.
Okay, so we can get the notes that you did today and the work that you did from the video itself.
Yeah, the videos will be up. If you look at the website, have you been to the website?
Yeah, the HCC.
No, have you been to our Canvas site?
Yeah.
So if you look at the bottom, it'll have like recent videos. And if you
Okay.
click on it, it won't be there immediately. I've got to post it, and it was giving me an error for the first video I did, but they'll be there in a like grid, and you click on it,
Okay.
and hopefully you hear my voice and you see my pen.
Okay. Thank you.
You're welcome.